It's you. Take it away.
So I'm not actually here to talk about PBKDF2. I'm here to complain about it. It comes from that era of RSA publications, late 90s, where most of them are kind of crappy. Like PKSys1 encryption, which was really crappy. RT4 maybe a little bit before, MD5 a lot before. They're all kind of knackered.
Yeah, it's on.
It's on? Can everyone hear me at the back? No. No?
Turn off the...
Let me just... Is that better? Okay, good. Right, did you get any of that? So I'm here to complain. PBKDF2, I think, has outlived its welcome. It comes from a historic background of broken crypto, and I think the various standards that were written to describe it, there are two, don't really tell implementers what is important and how to do what is important correctly. So with that, I'm going to give you a quick introduction to PBKDF2, and this may be kind of way below what a lot of people in this room already understand. So I have cats. I have a picture of my cat. Yeah. Then I'm going to describe why the standard is bad, and then I'm going to, as a direct result of that, I'm not blaming implementers because they've done basically exactly what is in the standard, that a lot of implementations are bad, and then I'm going to release some software. So the first, oh fuck, the cat's not there. My cat is missing. Right, so imagine there's a cat up there. She's a beautiful cat. So the
it's a secret cat.
Oh, I'm very disappointed with my cat. I was hoping to show off my cat. She's very pretty. So Merkle Damgard hash functions. This is construction for making hash functions out of this a relatively simple unit called a compression function, and you feed in your message in blocks with a particular size, and then at the end you get the result. This is a kind of simplification because there's some padding on the right that you have to do to make sure that messages going in are prefix free, but whatever. Next is HMAC, which is where you take one of these hash functions and you make signatures out of it. And it looks like that. This is probably the most complicated slide. So, yeah, if you can understand this, then that's great. So, going from the top, you start with your key, you XOR it with a block size constant, and you hash that, and then you hash your message. Separately, you hash your key, you XOR your key with another different block size constant, and you hash that, and then you hash the thing you originally got, and that's your signature. Very good. And then we come on to PBKDF2, and this is one of the problems, is that they try to be clever, and they try to parameterize the whole standard with this PRF, which the idea being that you can swap in and out different PRFs. In practice, everyone uses HMAC. I think Apple once used CMAC for something, but that was crazy of them. Yeah, AES CMAC, I think, for some weird reason. They have. Right. Yeah. So the main thing is you put a salt in the side and the password there, and you get a key out, and you can tune it to make it take a different amount of time. And yeah, it came from RSA kind of a long time ago. So this is the main slide. When you're using slow hashing, you come up with some kind of budget for how long you want to spend doing this, say 50 milliseconds, and then you work out how to tune this, the function you're using, to take exactly that time. And the problem is, if your PBKDF2 that you're using is, say, 4 to 10 times slower than it could be, then you're either giving a 4 to 10 times advantage to your attacker, who has like a boatload of GPUs, or you're just wasting the user's time and power and general energy, and it's just a disaster. So, yeah, the main thing that defenders want to do is maximum attacker work for the work that they have to do, and I think they're kind of failing at this. The rest of my slides kind of assume that all the salt and passwords are less than the block size. This is like 64 bytes, so it's generally true. And we're only going to take like the first hash outputs length of PBKDF2, because actually this thing, this capability of PBKDF2 is kind of crap and it's broken. I'll come on to that later in the last slide. So PBKDF2 looks like this. You get HMAC and you put the password in the top repeatedly, and you sign the salt, and then you sign the output and the output and the output, and you get all the signatures and you XOR them together, and that gives you your output. So it's fairly easy to see that this has very strong data dependency. So you can't calculate U3 without calculating U2, and you can't do blah, 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 blah. So you have to do them all in sequence. So it's not easily parallelizable by your attacker, which is nice. Well, yeah. So, yeah, there's some algebra at the bottom. I tried to remove most of the algebra. All these slides were 100% algebra, until someone who I gave it to a couple of weeks ago told me to draw diagrams instead. And this is the generalization of that previous diagram to a round which is neither at the end nor at the start. So the question is, how many compression function applications per iteration? Well, you can count them 1, 2, 3, 4. And this is what most people do. They go, there's 1, 2, 3, 4, there's 4 boxes, 4, excellent. But the standard doesn't tell you that this is kind of off by a factor of 2. There is one paper from a long time ago which points this out in passing. There doesn't seem to be a lot of documentation otherwise that tells people that they should be paying attention to this. The problem is that these two compression function applications don't have any data dependency to the others, and therefore what you do is you do those two first as a pre-computation, and then per iteration you only need to do these two. Yeah, this is not, so to be very clear, this is not a new result. This is known about by lots of people. It's especially known about by people with boatloads of GPUs, but I think it's slightly less known about by people who write Defender PBKDF2 implementations, which is the people I'm talking about mainly here. So yeah, you end up with 2 plus 2 i's for I iterations. This kind of begs the question of how Defender implementations are faring. So I looked at some. Interesting things on this slide. Script and the script. So script and the script, most people know, has a PBKDF2 pre-processing and post-processing step, but it only runs it with iterations 1. So it's kind of interesting, but it doesn't change script in any way. However, if you want PBKDF2, you probably shouldn't go and take theirs. And Apple Core Crypto as well, which was mentioned yesterday, I think. All the rest were from code review. This one's from disassembly because Apple hates freedom. I don't have that. So the winner is SJCL, Stanford JavaScript Crypto Library. And they win because I looked through the entire version history of the library, and they got it right from the very first commit. So excellent, very good job. That's what happens if you have your crypto library written by like a world-class cryptographer, I guess. Other people, OpenSSL and Python core. So these are basically they share the same code, written by a German Python core developer named Christian Heims, and he noticed this 2013 time and made sure that both were quite good. Django, Scoobs did the same thing, but in a kind of different context. So this CV was actually a denial of service. So one thing I didn't cover is if your password is very long, and you do a HMAC for each step with the key scheduling and everything, HMAC has to pre-process very long keys. And that means that if you send a Django web server, say, 0.5 megabyte of password, it will duly hash that every single iteration. And this will take minutes, hours of CPU time, and it will not end well. And then there's Bounty Castle and Apple Core Crypto. I cannot say whether Apple Core Crypto has always been like this or whether they fixed it. And yeah, so the rest are kind of just, are all relatively slow. FreeBSD is particularly interesting because that's disk encryption, but what they do is they measure at runtime how quick this thing is going, and then determine their iteration count based on that. So if it is really, really slow, you're immediately throwing away any advantage of having fast hardware by, you just give away a 2-time advantage to your attacker, and that's probably not what you wanted to do. So, don't blame implementors for this. This, I think, demonstrates, so ignore all these because this has been fixing the problem. Maybe Apple Core Crypto, I don't know. You can't say that one person has got this right and everyone else is incompetent. I don't think that flies. So don't blame them for doing this because they've done exactly what the standard said, and yeah. The next question is, how much practical difference does this make? Does a 2-time advantage, does it get lost in the noise? Does it, is it covered over by other inefficiencies, by slow compression function implementations and stuff? So, well, let's measure it for huge iteration counts. This all scales linearly with iteration counts, so whatever. And yeah, so back OpenSSL and Python 3.4, roughly the same because they're the same kind of implementation. And then there's the slow ones, PHP 5, which is not too bad. And then those two which are maybe twice as slow, kind of. So I wrote a patch, which is upstream for PHP 5, and that made it that quick. And I thought, well, that's quite good. It's kind of concerning that it's suddenly much quicker than OpenSSL, because in my brain, my opinion of the OpenSSL project is that they optimize for speed first, and that's basically it. Yeah. So if you imagine applying that improvement that I saw in real life to the other ones, then you kind of think maybe there's a slight a line happening there where it's kind of 12 seconds on this particular machine for that many iterations. But that result from PHP 5 got me thinking, well, why is that? Why is that kind of so much quicker, slightly quicker? And it turns out you can do a lot better. So that's the code I'm releasing today. It's there and it's public domain, so just take it and please take it away. And oh, it's on the last slide. I'll leave the last slide up. that's right.
Okay, the answer.
Yeah. So I thought I should illustrate why OpenSSL is so slow. Basically, this diagram is area per CPU time versus area. So on the right, there's fast PBKDF2, and you can see almost all the time, apart from a tiny blue sliver at the top, is spent doing compression functions. On the left is OpenSSL, and this beautiful cyan is the compression functions, and everything else is just random crap. And so, like, memory allocation, they do a memory allocation and a secure memory allocation and a free, so they clean everything out, and then they immediately copy the same thing back in every iteration. It's really great. Yeah. So hopefully this illustrates. So they spend 50% of their time not doing anything useful. Yeah. So I said that I kind of wouldn't talk about long PBKDF2 outputs because it's broken. And it's broken because, well, all defenders have to do this because they want the output, but most attackers don't, because if they're guessing passwords, then they can prove a guess from the first block, and if they know the format of your output, then they can say, well, the interesting thing I wanted is in the second block, so I'm just going to generate that and test that, and then if it's right, then I can generate the rest, and that's great. You can actually fix this with PBKDF2. You can glue different things onto the side. You can have a step where you spend time, make one block of output, and then you can have a step where you don't spend any time, you merely expand it. That's fine. That works. But out of the box, it's not good. But if you really do want that, and you're kind of crazy, and maybe you have a deployed system which just is dependent on this working, then this library, it's not a library, it's a single file, can parallelize this with OpenMP. And so I have a graph, which is the last graph. So here we've got OpenSSL for 1, 2, 3, 4 blocks. This is wall time now, not CPU time. And yeah, it's kind of 12 seconds, which was what on the last slide, and then 24, blah, blah, blah. And then, same thing, single thread, so the slope is less because it's quicker. And then, multiple threads, so this is on a 2-core machine, so you can see that between 1 and 2 blocks it doesn't take any more time, and that's because this is wall time. If it was CPU time, then it would kind of be going up as well. But and you can also see, I think due to the effects of hyperthreading, that the slope is less, so it's able to kind of parallelize, but not completely, some of the later blocks. So yeah, that's quite kind of interesting, because if you are using OpenSSL with 4 blocks, then there might be, say, 10 times performance difference between what you could achieve if you were willing to throw a couple of cores at it. And that's it. So I think it's a poor design. A lot of these things could have been fixed very, very easily with very small design changes. Probably which would have, I mean, some design changes that you could consider would ruin various security proofs applied to HMAC, say, the use of related keys and stuff, but whatever. It's described unhelpfully. They could have made a lot better job of saying, well, you should do this. To start with, pre-process the key, and then save the result, and then use that as a starting point on every iteration. That would have been really great. Most implementations waste time and power. I'm particularly interested in power because my day job is in mobile, and I think if you're not paying attention to power and you're developing apps, then your users hate you. They probably don't know it yet, but they do. And yeah, you can probably drop in a faster one, and that's your lot.
I cannot possibly imagine there are any questions or comments on this. Questions or comments? Steve was actually first this time, Jeff. Yeah.
So I asked you on Twitter, and you said that you were going to use vector instructions.
Right, yes. That's one thing I didn't cover. So, the whole implementation is designed in a way that everything is trivially inlineable. And that means that things like XORing together the intermediate values with GCC will get compiled to SC2 block XORs, so they're very quick. And the main thing is everything is available to the compiler, so it knows exactly what's happening. There are no function boundaries across compilation units where it can't optimize without whole program optimization, which is a disaster and no one uses it. One thing I would say is I'm not claiming that the thing back there is a performance record, because I think there's still some space to do that. And the main reason is, well, using OpenSSL's hash functions unchanged means there's some swapping back and forth of endianness. So the hash function input wants things in network endianness, and it wants to process them in host endianness. And so you have to kind of swap back and forth in the inner loop, and that's kind of annoying. It's not necessary, but I also don't want to start maintaining a load of assembler hash functions in all different platforms, because yeah, it's just boring.
Hi.
Sorry? Yes, I enjoy life and just not doing that.
I've got too many questions, so I'll try to. Well, then we can do that with I. Yeah. Okay. Okay. One quick one. Are you aware, or have you tested how any of this stuff works on Android? Or just porting? That just happens to be where I'm facing a bottleneck.
Yeah.
On PBKDF2.
So I think, right, there's a couple of questions there, I think. Bouncy Castle is quick, but Android has its own fork, effectively, of Bouncy Castle, which they haven't updated. So I did look at that, and it's kind of way, way behind, and it's slow, and it's eventually going to pull back down to some hash function implementation, which is also slow. So I'm not here talking for my employer, but we use OpenSSL PBKDF2 called through FFI, and that works, reasonably quickly. But to answer your main question, no, I haven't tested this on ARM or compared ARM PBKDF2, ARM OpenSSL PBKDF2 to my one. I expect kind of you get similar results. Yeah.
Okay, so I would say we should give him applause one more time. And you'll be around for some more time, I guess.
Oh, yeah.
Yeah, excellent. So now there's, the ability to relax. There's a happy hour in the chill-out room. We will be starting up here again at 5. The next speaker is Andrew Hintz from Google, and he